In this class, we are going to see in detail the Lagrangian formulation of classical mechanics. That is how the Lagrangian mechanics is developed from Newtonian mechanics, and we are going to see also the D'Alembert principle in detail. Before going into the detail of D'Alembert principle and Lagrangian mechanics, we will see some fundamentals of Newtonian mechanics. Uh, that is, we know the Newton's second law of motion, which is F equal to ma, is a dynamic problem. Newtonian mechanics provide a comprehensive framework to analyze the various type of forces, motions, motion and interactions between the object. It is more general and can be applied to a wide range of situations, including non-inertial frame. That is, your reference frame may be inertial or non-inertial. Non-inertial means that is accelerating frame. You can apply this to accelerating frame also. With this understanding, we will move on to D'Alembert principle and Lagrangian formulation. Before going into the detail of D'Alembert principle, we will see some fundamental about the virtual displacement and virtual work. The virtual displacement are infinitesimal small and do not violate any constraint or condition imposed on the system. It's a very small displacement. By considering the virtual displacement, the work done by the force acting on the system can be calculated. This is the important point. That is, we can calculate work done by the force by using the virtual displacement. The principle of virtual work states that if the system is in equilibrium, the total virtual work done by the internal and the external forces on the system is zero. In the case of virtual work done by the system due to both internal and external work is zero for any arbitrary virtual displacement. And this principle allows to analyze the forces and motion of a complex system by setting up the equation based on work done by the individual forces. Before going into the detail of virtual work, we will try to understand what is virtual work. Let us consider that I am applying the force along the positive x direction as shown by green color arrows. Of course, I am applying different type of forces. Like I have shown this arrow. See, the total force is F equal to ma. This is the square object, blue color, which I have shown in blue color is the object. I am applying equal and opposite forces in the other side, as shown by the red color arrow, so that this object is under equilibrium condition. This force is equal to minus F equal to minus ma. So this force is called inertial force or fictitious force or D'Alembert force. So you can call it as a fictitious force or inertial force or D'Alembert force. Uh, Unlike Newtonian mechanics, it is D'Alembert's principle is limited to the system in equilibrium or steady motion and does not address the general case of accelerating system. See, this is not an accelerating system. We are going to find the this big, inertial force. Inertial force. Finding inertial force under equilibrium condition is easier than the force comparing in a dynamic system. This is not dynamic. This is a static system. Static system means the object is at rest or it's slowly moving one. We generally formulate the laws of mechanics in such a way that work done by the forces of constraints. In previous class, I have explained about different type of constraint. So here, work done by the forces of constraint is zero when the system is in motion. We are going to see within a couple of minutes about this. For the force of constraint Fi, the work done for the infinitesimally small displacement delta Ri is zero. That is work done. The small work done delta W is equal to Fi dot delta Ri, which is equal to zero. By definition, the forces of constraints are workless forces. So here, this is another important point. The example for the force of constraint is simple pendulum. See, your bob is moving along this. Uh, then you know very well that the movement is along this direction. It will form a circle like not a full circle, it's a semicircle. It will because this length is fixed. But the tension of the string is perpendicular to the motion. So what is work done? Force into force start distance. So it is if it is parallel, you will get maximum work done. But here the force and work done are perpendicular to each other. So naturally, the work done is here is zero, and this constraint also time independent constraint. That is also a very important point. So, irrespective of time, there is a constraint. It cannot move beyond L. This is uh, the string length is L. So, you can keep it in your mind. This is the best example for the virtual forces of strain and the virtual work or workless process. This is. Now we will see the principle of virtual work. The work due to virtual displacement is known as virtual work. By the principle of virtual work, a system with workless constraint, just we have seen, is in equilibrium under applied force. If and only if zero virtual work is done by the applied force in an arbitrary infinitesimal displacement satisfying the constraint. Just we have taken the example of simple pendulum. So pendulum moves along the direction along the string L, and the force is exerted perpendicular to the displacement of the pop. So naturally the work done is a dot product. Work done is equal to zero because it is a perpendicular direction. Force is in perpendicular direction to the displacement. So naturally it will be zero. Let us now consider a dynamical system which is in equilibrium. Then from the total force of each particle of a system vanishes. That is total forces is equal to zero. Fi is equal to zero. Now, let us give a virtual displacement to the system. Then the virtual work of the ith particle is that is Fi dot delta Ri, where delta Ri is the virtual displacement of the ith particle. So the total virtual work of all particles is summation over I Fi dot delta Ri, which is equal to summation over I Fia. Here the superscript A represents the applied work multiplied by this is actually dot product delta Ri. We have splitted the force into two part, that is applied force and this virtual force, that is Fi, internal force, F of I, summation over Fi dot delta Ri. Since this is the virtual force, the work done by the virtual force under small infinitesimal distance is under virtual displacement. Actually, it's a virtual displacement is equal to 0. Just now we have seen. So we can cancel out the second term. So which is equal to 0. That means the summation over I f I dot delta Ri is equal to summation over I fi a dot delta Ri is equal to 0 because this second term goes away. So it can be simply written as summation over I FIA dot delta Ri is equal to 0, where FIA is the applied force. This is the principle of virtual work. Just now, we have seen the condition for equilibrium of a system that the virtual work of the applied forces vanishes. That is summation over I FIA dot delta Ri is equal to 0. The above equation is often called principle of virtual work. uh, we know f of I, that is force is nothing but is equal to rate of change of momentum, that is time derivative of pi. So this is the force equation. In other words, Fi is equal to ma. This is nothing but Newton's law. So if you bring pi dot in the left hand side, we will get fi minus pi dot, which is equal to 0. If you see mathematically, uh, both look like the same, one among the same. But however, the physics differ. Uh, the physics of two equation is different. Here, F equal to ma is Newtonian mechanics. Here, Fi minus ma is equal to 0. This is the uh, law of motion under equilibrium condition. That is F minus ma is equal to 0. That means it's the equilibrium condition, which states that particle in the system will be equilibrium under a force equal to actual force plus a reversed effective force. Just now I have explained reversed effective force is nothing but inertial force or D'Alembert force. So this is the reverse the effective force, which is minus pi dot. So just now we have seen Fi minus Pi dot is equal to 0. This is the another form of Newtonian mechanics where F equal to ma. So we are writing the other form F minus ma equal to 0. F equal to ma, F minus ma equal to 0. Both are same mathematically. But physical aspect, there is lot of difference. So F equal to ma is applicable under any condition. It is dynamic. As I said, it is valid even for non-inertial frame of reference. That is accelerating problem. However, this D'Alembert principle is applicable for static case. Uh, of course, static or dynamic in equilibrium. That is very important. It is a static process or dynamic in equilibrium process. So that is very important. The advantage of D'Alembert principle over Newtonian mechanics is Newtonian mechanics is applicable for all condition, all situation. Here it happens in equilibrium condition, so it is very easy to solve a complicated, complex system, whereas Newtonian mechanics is a very simple method, simple, straightforward method. Here it is our D'Alembert principle is applicable for a complex system. Here, as usual, Fi, the force I am writing into two parts. One is applied force Fia plus the internal force Fi or inertial force Fi, small fi. But I have already explained to so many times the work done due to the inertial force is zero, so you can eliminate the second term, that is Fi. So as we have seen that summation over I Fia minus Pi dot uh, whole thing multiplied by is a dot product delta Ri is equal to 0. So after removing this small f, you will get this expression. So uh, you know what is pi dot? Is nothing but rate of change of momentum, which is equal to mass into acceleration. That is, acceleration can be written as r double dot. R double dot is nothing but acceleration. That is second order time derivative of distance. So which is equal to 0. This above equation is called D'Alembert equation. Uh, in due course, we will see the Lagrangian equation and their advantage over Newtonian mechanics. Now we will compare the Newton's second law and D'Alembert principle. Newton's second law states that F equal to ma. As I said, it is for dynamic system. In D'Alembert forms, this is equal to F minus ma equal to 0. That is, it implies, as I said, is so though mathematically both are same. There is a difference in aspect of physics. That is, it shows the force which act on a stationary object. That is the object at the equilibrium, or that is either at rest or is slowly moving on. So this can be generalized as summation over I. That is, we are dealing with the infinitesimal moments. So we will see the force in that is work done. In this case, force into distance. So work done is equal to 0. We are moving the small infinitesimal distance delta Ri. So you have to sum it over I. Then summation over I A indicate applied force minus Fi Ri double dot. This is acceleration. Uh, with dot product of delta Ri, which is equal to 0. So that D'Alembert principle reduces the a problem in dynamic to a problem in statics. Because unknown forces are more easily determined on a body in a equilibrium. So, so this I have already explained. We can easily determine the forces which act on the body under equilibrium condition than on a body on a moving bodies. The force and the stress analysis of the machine component can be usually be simplified by using the inertial forces. Now we will move on to Lagrange equation from D'Alembert principle. From D'Alembert principle, we have got this expression summation over I FIA minus MI RI double dot dot product with the delta RI is equal to 0. Here, in rest of my lecture, for mathematical convenient, I am going to write FIA as simply FI. This equation does not necessarily means the individual term of summation are zero. That is, each and individual terms are need not be zero. Say if I is equal to 1, this may give some value, I equal to 2, this may give some value, some other value. It need not be zero all the time. But how to make it zero? That is our ultimate task. We want to express this relation in such a way where all the terms in the summation become individually zero. Let us take this expression u1 delta x1 plus u2 delta x2 is equal to 0. This is valid only x1 and x2 are independent. That is, by changing x1, x2 will not change and vice versa. So in that case, if you want to have that relation, then u1 and u2 must be equal to 0 for all possible x1 and x2. If there is it is not independent, x1, x2 is not independent, then by changing x1, x2 will get changed. So we have to use the different coordinate system. Say, for example, Cartesian coordinate is very simple to use, x, y, z. But it's depend, R value depends on x, y, z. But however, if you take this spherical polar coordinate, r, theta, phi, both all three are independent. Theta, by changing theta will not affect r, and changing pi will not affect theta, like that. We will see it in detail. So this is our expression just now we got from D'Alembert principle. Uh, then I have raised the question how to express this relation so that individual term in the summation are zero. For that, we have to use the generalized coordinate system as they are independent. Just now I told that x if you are using a Cartesian coordinate system, then the x1, y1, z1 will change when particle moves with different directions. So x1, y1, z1 will change. So it depends. The r value depends on x, y, z coordinate. However, if you use the spherical coordinate system, then that is r, theta, pi. So all three coordinates are totally independent. By changing r, theta will not change. By changing theta, pi will not change. So we can use the generalized coordinate system. Consider a system of n particle. The transformation equation for the position vector of ith particle r. Here I indicate ith particle. Ri is equal to Ri, which is a function of q1, q2, q3. It will go up to qj to qn, qj, and it will go up to qn. Of course, there is a time difference. So where Q's are the generalized coordinate of the system. From the above equation, we can write delta Ri is equal to uh, a partial Ri over partial Q1 into delta Q1. Like that, it will go partial Tri over partial Tq2 into delta Q2. It will go up to. Of course, the last term is time dependent term. Uh, Partial Tri over partial T into delta t. We have seen so many times that for infinitesimally small displacement, uh, it this displacement did not depends on time factor, so it will be zero. So you can ignore the last term. This last term can be ignored. You can remove this last term, so this can be written in the summation form. The delta Ri is equal to summation over j 1 to n delta Ri over delta Qj into uh, delta Qj. This is see here, everywhere there is Ri. So here running index is only the j. So this is the D'Alembert expression equation. Now let us take the first term, that is summation over I fi into delta Ri, first term delta Ri. This can be written as, just now we have seen that delta Ri, which I have shown in red color font, can be written as partial Ri over partial T Ri over partial T Qj into delta Qj with summation running over J. Just now we have seen this. Of course, this Fi is running in that this I, summation over I. This is the this expression can be first term of this expression can be written like this. Now you take the term inside the bracket, this term, that is you take this term inside the bracket, that is summation over I fi, this partial derivative term, that we are redesignating as Qj. So the Qj is called generalized force. So instead of Fi is replaced by Qi, where Qi is equal to Fi dot partial Tri by partial Tqi. So this is the generalized force. So the first term of this equation is can be written as summation over I Fi dot delta Ri is equal to summation over j, because no I involved in this right hand side, Qj into delta Qj. Now we will see how we arrived at this right hand side. So you take this time derivative of mi ri dot partial tri over partial tqj. Now you differentiate. First you differentiate this Ri. So because mass is a constant, so you differentiate Ri. Of course Ri dot. So this will become Ri double dot. Then you keep the partial derivative term as it is. Next, what you will do is you keep first two term mi Ri dot as it is. Then you differentiate this partial derivative term. So this will become t partial time derivative of partial time derivative of partial tri over partial tqj. You will get like this. Now what I am going to do is I am going to bring this second term to the left hand side. So this plus will become minus. Now you compare this equation and this one, the second one. Mi r double dot multiplied by tri over tqj. This one, this left hand side is equal to this right hand side. So it's a very simple proof. Now we will do the further simplification. Finally, we arrived at this expression. Just take this term, partial derivative term. Partial Tri over partial Tj is can be written as That is, you are dividing this by partial partial d by here also partial d. So dri over dt is equal to nothing but the velocity. Rate of change of displacement is nothing but velocity. Similarly, dqj over dt is nothing but q dot. Dot represents the time derivative. So this can be written as this blue color term dri over dqj can be replaced as dvi over dq uh, dq j dot. So this can be this blue color tab can be replaced by this. That is what I have done here. Similarly, in the second term, you can see. In the second term, that is green color part, uh, time derivative of partial derivative, partial TRI over partial QJ is equal to. Now here I have changed the operator. Time derivative was, here comes first in the right hand side, it comes second. So I have interchanged this operator, differential operator. First one to second, second one to first. In case of classical mechanics, we can change the order of the operator, that you know. However, if it is in quantum mechanics, you are not supposed to change the order of the operator because there are a lot of uncertainty comes. So I have changed the order of the operators. So this is the time derivative. So TRI over TT is nothing but VI, velocity. So this can be written as partial TVI over partial TQJ. So I have replaced this green part by this. So we got this relation. Just now we arrived with this expression. Now you can take right hand side and rewrite it. You take the summation over j outside. Uh, then you can take d by dt, that is time derivative, which I have shown in red color band, and you take delta over delta qi qj dot outside, because there is no running index with the I. So I am keeping the uh, I terms inside this summation over I. So I have separated I and J. So summation over I of Mi, this R dot, Ri dot is nothing but Vi, and of course, you know, this is there is Vi here because we have already taken this derivative outside this summation. So this is Vi. Then you may ask the question how this half comes. See, when you differentiate this, Mi into, sorry, Vi into Vi is Vi squared. If you differentiate with respect to time, then you will get 2 Vi, 2 will get cancelled. So because of that, I have introduced off here. Similarly, the second term, summation over I have taken this blue color bond, T over TQJ. So this I have taken blue color outside, like the red color bond term outside. I have taken here the blue color terms outside. Delta over delta QJ, summation over I. Here Ri dot is Vi. Here already one Vi. This up because I have already explained. If you differentiate Vi squared, you will get 2 Vi. Because of that, this off comes here. So this off Mi Vi squared is nothing but the kinetic energy. This can be replaced by the term kinetic energy. That's what I have done it here. T by dt of partial t over partial t q j dot, because this t represents this of me square. Similarly, in the second term, the summation over of MIVI squared is the kinetic energy. You may ask the question where the summation terms goes, summation over I. This T represents the capital T represents the total kinetic energy. So finally we arrived. So this is the left hand side. I have taken this left hand side as it is, and I have replaced this right hand side by this one. This is what we have arrived now. We will see what will happen to this. Just now we have seen this expression. Just what I am going to do is you multiply by delta qj both side. Delta qj, here also delta qj. You know here this green color bond, that is delta Ri over delta qj into delta qj is equal to delta Ri. This green color bond parameter I have replaced by delta Ri. Now what will happen to this expression? We will see. Just now we have arrived with this expression, and also you remember that at the beginning of my lecture, I have shown that summation over I fi dot delta Ri is equal to summation over j qj dot delta qj, where qj is the generalized force or conservative force. So, which is equal to this one, which can be rewritten as, see, I can bring this to the right hand side. So, this will become minus q summation running index here also j, so summation over j minus qj. Of course I have taken delta qj outside, delta qj outside, which is equal to 0. This is our expression. Just now we have arrived. Here you remember that delta qj is virtual displacement. Uh, this virtual displacement is independent of another virtual displacement delta qk. That is because both are independent. Delta qj is the virtual displacement which is independent of delta qk, and therefore separate coefficient vanishes. So individual coefficient vanishes because is a virtual displacement is independent of each other. So this can be rewritten as uh, time derivative of delta t over delta q dot minus delta t over delta qj, which is equal to qj. This term. The above equation is one form of Lagrange equation. We will see the final Lagrange equation in within a few minutes. So we have arrived with this expression. Um, However, we know that the force is defined as negative gradient of the potential. That is well known fact. Uh, but by definition, Qj is equal to summation over Fi dot Tri over Tqj. So which is equal to, now I am replacing Fi by this one, negative gradient of potential V. This gradient is a, partial derivative with respect to position. So this gradient V can be written as delta V over delta Ri. Here delta Ri will get cancelled. So Qj is equal to minus delta V over delta Qj. So now I am going to replace this green color bond here. So this expression will come time derivative of delta t over delta q dot j minus delta t over delta qj is equal to minus tv over delta qj. Just now we have seen this expression. Just you bring this minus delta v over delta qj to the left hand side. Here this will become here also the second term is a partial derivative with respect to qj. This term also partial derivative with respect to qj. So this will become minus delta t minus v over delta qj, which is equal to 0. Uh, so the equation of motion is not restricted only to the conservative system. Moreover, uh, this potential does not depends on the velocity. You know very well. Neither it depends on time or velocity. Here the first term contains the time derivative as well as the velocity derivative. Q dot is velocity. So potential is independent of both. So I have introduced t minus v here because it will not affect your result. So finally we got this expression. We will see what will happen to this. So this is the expression we got. And now we are going to define a new function called Lagrangian L, which is equal to t minus v. So I am replacing t minus v by L. Normally, the total energy is equal to the sum of the kinetic energy and potential energy. Here, there is a difference between T minus V, that is kinetic energy minus potential energy. Lagrangian is nothing but the difference between the kinetic energy and the potential energy. That is very important aspect. Significant of this is we are dealing with a infinitesimally small displacement. That is the virtual work is 0. So which is going to have a least action, principle of least action. The entire classical mechanics depends on the principle of least action. That is, we are dealing with infinitesimally small displacement. So it has its own significance. That is the difference between kinetic energy and potential energy. If both are the same, then it is almost under equilibrium condition. So finally, we arrived with this expression. The above equation is called Lagrange equation. The Lagrange mechanics is that it can be used to solve almost any mechanics problem in a systematic and efficient way. So we will see the important point about the Lagrangian equation. This Lagrangian equation involves only kinetic and potential energy, which are scalar quantities. That is L equal to T minus V, kinetic energy minus potential energy. So hence we have developed our mechanics such that we do not require all the information about the forces which were necessary in Newtonian dynamics. Uh, when we transform from space coordinate system into a general coordinate system, the forces remains invariant. That also we have seen now. The Lagrangian L, which is equal to T minus V, is invariant under coordinate transformation. Normally, to find the total energy, we will add this potential energy and kinetic energy. So here we are finding the difference. That means uh, this T minus V must tends to 0. We are going to see this is the principle of least action when we are dealing with the Hamiltonian mechanics. We will see the importance of this Lagrangian in Hamiltonian mechanics also.